Oh, there we go. Okay, we're recording. So hello, thanks so much for having me. I have been there a few times. As Anna said, I went to Wellesley, so Harvard was always close by, but hopefully I can come and visit again in the future. I've been working on massive stars for the past around 10 years, primarily with Phil Massey at Lowell Observatory, and now most recently with Emily Levesque at University of Washington. And today I'm going to talk about my thesis research, which is primarily on the binary fraction of red supergiants. So there we go. Red supergiants, very brief overview, are evolved massive stars. They come from 8 to 30 solar mass OB stars on the main sequence that finish burning through their hydrogen. They rip across the HR diagram and very quickly become yellow supergiants before kind of ending their lives as red supergiants, and then for the most part exploding as supernova. And they are, as you can see here, incredibly luminous and incredibly cool. And they are important to study because when they do explode as supernova, they enrich the surrounding interstellar medium with these nice heavy elements that help create the solar system and what we are made of. So understanding their evolution and their numbers, their population statistics is really important for understanding kind of how our universe is populated with these heavy elements. And so today I'm going to be talking primarily about the binary red supergiants, and these are important because the evolution of any type of star, in particular massive stars, is highly constrained and altered by binarity. And so if you have two stars in a binary system, if they're close enough and they're interacting, so maybe one is stripping material off of the other, it's going to change their evolution, how long they live, and maybe even the percentage of heavy elements that they kind of deposit when they turn into a supernova. And binarity is especially important in massive stars because we are continually learning more about how many massive stars are in binary systems. The numbers are high, still not perfectly constrained, but if we kind of go to very close, very interacting systems, such as spectroscopic systems, we have 30 to 35%, and as you kind of get further and further apart, the numbers go above to 60, 70, maybe even up to 100%. So many, and this is for the unevolved OB stars. So many massive stars are in binary systems, and so understanding them is incredibly important for understanding stellar evolutionary theory. So when I started this research around 2018, a few years ago, not very many red supergiant binaries were known and characterized, and the number was really around a dozen in our own galaxy. And so this is kind of because it's difficult to find these things and learn a lot about them. And so they vary. We've probably all heard the talk about Betelgeuse earlier this year, pre-pandemic times. It dimmed, and that was very exciting. And kind of the current theory is that it belched out a lot of dust. And so this kind of blocked it in the visual magnitudes. And so this is common. Red supergiants have these episodic mass loss events. They also have these pulsations that make them vary on the order of a magnitude in V. And they have these huge convective cells. And so here is a nice little simulation by Chiavasa that shows just these huge convective cells that are larger than our sun and vary on the order of weeks to months to years. So if you do kind of the standard, let's take a light curve of a red supergiant and see what happens, you're gonna see a lot. And it's gonna be really difficult to tell what of that is coming from maybe a binary companion versus these mass loss events, these variations. Also, In terms of looking at radial velocities for determining binarity, the periods are very long. These stars are huge, thousands of solar radii. And so you have to have very long baseline spectroscopy to try and find variations. And so even just determining if they're in binaries from kind of the traditional methods is quite difficult. So my first project was basically, well, if these stars are in binary systems, what would their companions be? What type of, and primarily stellar companions? And so from this, I just kind of used basic evolutionary theory. So red supergiants come from 8 to 29 solar mass stars. Stars that are on the main sequence and less than this don't evolve into the red supergiant phase. They're not massive enough. And OB stars, generally O stars, more massive than this, will generally go directly to the Wolf-Rayet phase and not pass through the red supergiant phase. So I wanted to look at basically how long will it take the least massive of these to evolve into a red supergiant. And so it'll take around 8 million years. And so it'll take this amount of time for a star to stop burning through its hydrogen and briefly go through the yellow supergiant phase before becoming a red supergiant. So then what type of star could be in a system with this star? And so it takes a 3 solar mass star around 7.2 million years to even enter the main sequence. So before this, it's a protostar. And so it then kind of follows that any star less massive than 3 solar masses will not have formed. It'll still be a protostar by the time this, basically the least massive red supergiant forms. And for those of you who think in terms of spectral type, this is around an A0 dwarf. So basically main sequence stars less than 3 solar masses are still going to be protostars, and it's going to be kind of hard to form for a protostar to form into a real star when it's right next to a red supergiant, because again, red supergiants are huge. In many cases, they'll be engulfed in the red supergiant. And so it then follows that red supergiant companions will primarily be B-type stars. And there might be some O stars, some higher mass stars, maybe some Wolf-Rayets, other red supergiants, but just based off of the IMF, these are going to be a lot less common. You know, the number of B stars way overshadows the number of O stars in the universe. And so luckily, this is one of those great instances where evolutionary theory and observations match, and all of the known systems are red supergiant with B-star companions. And so here are 5 of the Milky Way ones. Again, there are around a dozen of them. And so we can be happy that, you know, I then went and did a literature search and tried to find all of the red supergiant binaries, and lo and behold, they all had B-star companions. So this made me very happy. So now I want to find them. And so the first method, the kind of obvious one, is spectroscopy. And so let's look at spectra of red supergiant and B stars. Here we have the spectrum. This is a Marx model of a M6 red supergiant. And the main thing to take away are these incredibly strong titanium oxide bands, and they are kind of indicative of red supergiants, at least at visible wavelengths. And so these happen because the stars are so cold that molecules can form. So these stars are 3,000 to 4,000 degrees Kelvin. And when we look at a B star, main takeaway is these strong upper Balmer lines. And so very strong red or blue words of around 4,000 angstroms, and indicative of kind of a B star or an O star, also obviously A stars, but in this case, we're looking for B stars and maybe some O stars. And so I then ran a bunch of models to combine synthetic spectra. For the B stars, I used the B stars 06 models. For the red supergiants, I used the Marx models, and essentially created all these little examples of what maybe a binary red supergiant would look like. And so different combinations of temperatures and luminosity classes for the B stars and, you know, temperatures for the red supergiant. And so here we have two examples where the red supergiant is in red, the B star is in blue, and the combined spectrum is in black. And the thing to notice is that in these cases, you can see both these titanium oxide bands and the strong upper Balmer lines. And so you should be able to see kind of both components of the spectrum. And so then I went through some archival data, because when people are looking at red supergiants and trying to classify red supergiants, I have found that they are generally looking in the red, because that's where red supergiants are bright. And so a lot of people find the titanium oxide bands, and my Phil Massey and one of his previous summer students had a couple hundred spectra of red supergiants in the Magellanic clouds, and they had done a great job looking at those titanium oxide bands, but they had never really looked in the blue. And so I went back through that spectra and looked in the blue and found that a lot of them had Balmer lines. And so here we have this nice, beautiful example of a red supergiant B-star binary in the Large Magellanic Cloud that we had spectra of and had previously been overlooked because we just weren't looking for it, the blue Balmer lines. And so spectroscopy is great, and as an observational astronomer, I would love if we had spectra of everything in the sky, but obviously that's not reasonable. And so it's expensive, and generally photometry is easier to come by, especially when you're looking on galaxy-wide scales. And so my next step was, what's an easier way to find these stars if we can't get spectroscopy of everything? And so I went to photometry. And the principle is pretty basic. Red supergiants have more flux in the red than in the blue, and B stars have more flux in the blue than in the red. And if you combine the two, then photometrically, a red supergiant B star binary is going to look quite different than a red supergiant or a B star by itself. And so it'll have a different photometric signature. And so we can plot this on a color plot. And so we have U minus B on the x-axis and R minus I on the y. And all of the B star, the B star 06 models are the blue points, and the Marks red supergiant models are the red points. And then the combined spectral models are these black, as Emily Levesque would say, the duckbill diagram. And so photometrically, that's where these red supergiant B star binaries should exist. And we can now plot actual stars on this. And so the magenta points are spectroscopically confirmed red supergiants in M31 and M33, where the data comes from Phil Massey's local group Galaxy survey. And then the cyan points are B stars. And so they fall about where you would expect from the synthetic spectra. And so this little red triangle region is where I think the red supergiant binaries should exist. And so to try and kind of determine if my hypothesis was correct, I went out and I took a bunch of spectra of stars with photometry in that nice little region. And so I looked at stars in both Magellanic clouds by going down to the MMT going down to Magellan and observing stars there. And then for M31 and M33, I went to the MMT and used hectospec. And so I found 250 of these. And so in the course of around 2 years, we went from 12 known in our own galaxy to 250 known in the local group galaxies of M31, M33, and the Magellanic clouds. And it was great because that meant that those photometry cuts I was using were working, and this would allow us to find and better characterize these red supergiant binaries. And so next, I wanted to look at kind of a galaxy-wide scale, I work a lot in the local group galaxies because, especially for massive stars, they're generally bright enough that you can get complete populations down to some limiting luminosity of all of the stars. And so this allows me to do things like the binary fraction. And so to do that, obviously, I first needed to know all of the red supergiants in order to, be able to divide and determine the binary red supergiant fraction. So to do that, we turned to the LMC first and near infrared photometry. And recent advances have allowed us to now reliably separate out the red supergiants in the Large Magellanic Cloud or any galaxy from the brighter AGB stars. And so Gaia obviously allowed us to get rid of the foreground stars, which was huge advantage and has been wonderful for my research. And after taking out the foreground stars, recently Ming Yang realized that there are basically these two different distributions that allow you to determine which ones are AGB stars and which ones are red supergiants. And this is pretty exciting for red supergiant research because previously we would only go down to, in this case, a limiting magnitude of around 9th in K, and now we can go much, much lower because we can separate out these bright AGB stars. And so this shows kind of the different regions of AGB stars and red giant branch stars and the red supergiants. And then the black triangles are spectroscopically confirmed red supergiants in LMC by Emily Levesque and Phil Massey. And so this allowed us to come up with a complete sample, at least down to a limiting luminosity of red supergiants. And I then wanted to determine which ones of these were binaries. And so I observed a lot of them to determine which ones were single stars and which ones were binaries, but I then wanted to kind of generalize this to the rest of them. And so for that, I used a k-nearest neighbor algorithm that took a bunch of photometry as kind of the input. And so the general idea is that red supergiant binaries should have some sort of blue excess. And this is what we see on the left. We have color plot where the blue stars are binaries and the red ones, the dark red ones, are single stars. And you see that the binaries have much lower U minus B values. And then also I used Galaxy imaging, which is UV photometry and allows you to tell if, the red supergiant has a very bright UV source next to it. And if it does, then that is indicative of a B-type companion. And so I used kind of all this input information into the k-nearest neighbor algorithm and then was able to classify the red supergiants where I didn't have spectra of them. And so the result of that is shown on the right, and the color corresponds to the probability of it being in a binary system where the redder stars are more likely single stars, the bluer stars are more likely binaries. And so this allowed me to get an observed red supergiant binary fraction of at least the OB stars. And all of the initial synthetic stuff I did was for B stars, but O stars would be included in there as well. Spectroscopically, it didn't appear to find any, but it's possible that, you could have a red supergiant O star binary, just much, much less likely than red supergiant B star binary. And so the observed binary fraction was quite low, around 14%, and then largest errors because k-nearest neighbor algorithm isn't perfect, but I went down to a log luminosity greater than 4, less than this, and I don't believe I'm complete and might be contaminated by some AGB stars, but the total number of red supergiants was 1,800. And so obviously this was the observed fraction, and so there are some things that I wanted to correct for, and so that my observations were kind of biased against. And so for that, I used BPAS, which is a binary population synthesis and evolution code that deals specifically with binary stars, and it allowed me to estimate the binaries in eclipse and the binaries with compact companions. And so this brought me to a total binary fraction of around 20%. And so first thing that I thought is that's really small. The OB star binary fraction is much, much larger. Where did they all go? Red supergiants come from OB stars. But the basic explanation is that red supergiants are really big. And so there's a lot of mergers that are going to happen. OB stars by themselves merge. And so when you then have the more massive star expand, then you're going to get even more mergers. And so just to show this in terms of pictures and animals, here we have my dog, Meg, playing the role of the red supergiant, and my cat, Marlowe, playing the role of the B star. They're going to start off separated, and then over time, they're going to move closer and closer together as they become more gravitationally bound. And the red supergiant is going to continue to expand, and then eventually they will merge, and you'll just be left with a single looking red supergiant. And so basically, only in the most separated systems, there will be a red supergiant binary. And so this is why the fraction is so small. And so just really quick, one more point I want to make. I also wanted to look into changes with metallicity. And so metallicity very strongly affects the evolution of massive stars. It changes their lifetimes, how they evolve. And so could this change the binary fraction? And it doesn't seem to change the Wolf-Array star binary fraction, but what about for red supergiants? And so to do this, I did all the stuff I just talked about for the LMC, except for I did it for M33, which has this huge metallicity gradient. And I found this, which made me happy and sad. So the inner part, rho by like 0.1, has a kind of solar, maybe a little super solar metallicity. And then the outer part, so this is just distance from the center of M33, has a metallicity that's around a quarter solar. And there is a gradient there. Something is going on. And I didn't expect this, but it's there. And this is now, I found this a couple days ago. And so this is my very new research that I'm now thinking about a lot. And so main thought is we don't know a whole lot about whether the OB star binary fraction is metallicity dependent. And so maybe that's what's happening, is that kind of the parent population is. And so this is definitely a stay tuned, and hopefully in the next couple of months before I try and defend my PhD, I'll have this more figured out. So key takeaways: red supergiants preferentially have B-type companions. We found over 250 of these in M31, M33, and the small and large Magellanic clouds. And the binary fraction appears to be decreasing with metallicity, and that's still a question that I am pondering. So thank you so much. And again, thank you so much for inviting me. And I am more than happy to ask or answer any questions. Thanks.
Great, thanks, Kathryn. That was a great talk. I really like the illustrations. I think using pets to illustrate astronomy concepts probably one of the best ways to do it. I have used my cat as an example about massive star formation in talks. She's a big cat. Okay, so we got a couple of questions. So let's start with Andrea Dupree.
Yeah, I have the chat open if you just want me to.
Oh, great.
Yeah.
Oops.
So Andrea asked, Betelgeuse is rotating faster than we expect. It has been suggested that it's consumed a companion that increased its angular momentum. What do you think of that? Are there any spectroscopic signatures? This is perfect. So this is exactly what I'm working on now. I am looking at, so yes, you would expect the rotational velocity to speed up. Generally, red supergiants have very, very small rotational velocities, at least in terms of massive stars, of around 5 kilometers per second. If they've merged, they should have rotational velocities of maybe closer to 10 or 15 kilometers per second. And so this semester, I am observing galactic red supergiants, hopefully around 50 to 75 of them. using Express, which is mostly for planet finding, but it's a very high spectral resolution spectrograph out at Lowell Observatory's 4.3 meter. And so I am trying to determine rotational velocities to figure out if the red supergiants have merged. And in the perfect world, which we all know will never happen, I hope to find their rotational velocities and then make a histogram. And in the perfect world, maybe there will be two distributions, and one will be close to 5 and they will be the single stars, and one will be close to 10 to 15 kilometers per second and they will be the merged stars. And that would be wonderful, but it will at least, you know, help us learn a lot more about red supergiant mergers. And so another question from Charlie Conroy: do you worry about contamination from projection effects within the photometric aperture? Yes, I actually did. I did worry about this, and I did some Monte Carlo simulations where essentially I looked at kind of the crowding of all of the stars and the Zariski's photometry, also what are like the 1 arcsecond apertures on Magellan, and I think it's 1.5 on MMT, and just to determine like what, if line of sight could be an issue. I found that it was very, very small. And so that was for LMC. I have not done this yet for M31 and M33 because I just started on that project. It's probably going to be a little bit bigger because they're further away. But I found that A, it was small, and B, it was, the numbers were exactly the same for both the binaries and the single red supergiants. And so I don't believe this is contributing to the effect, but definitely something worth taking into account.
I actually have a question. Have you looked at the like mass ratio distribution? Like, so can you extrapolate for the red supergiants to figure out what its initial masses were, compare it to the B stars to get an idea of what the mass ratios are?
I haven't done too much with the kind of physical properties yet. I'm able to get kind of physical properties for the red supergiants because I have for the ones that are the spectra is flux calibrated, I'm able to get, you know, spectroscopic luminosity and temperature estimations from the ones that aren't. I can get stuff from the near infrared. The problem is that I really can't get too much about the B stars because I only have the upper Balmer lines, and spectrographs are generally not great in the blue. And so I really, it's just if they're there or not. I did try doing some modeling, but it's so contaminated by the red supergiant, even down there. I did put in an HST proposal last year and got declined, so I'll put it in again to get UV spectra of the B stars to then try and figure out all of the ones that are known in the galaxy are B dwarfs. Based off of their photometry, there should be, some of the ones that I found should be B supergiants. And so it would definitely be interesting to try and learn more about that, but it's really hard with what I have, and I really need uncontaminated spectra of the B star, and so I need UV spectroscopy, which okay, you know, is fun to try and get.
Yeah, great. We have time for 1 or 2 more questions. Does anyone else have any questions? Well, that's exact. Oh, got one. Actually, okay, yeah, I guess so. I guess I'll just follow up with that then. I guess another question I had is, with the merging, would you expect the spectra of the red supergiants to be contaminated? So like to have a different spectral signature?
It's possible. It's never, I mean, yes, hypothetically, you should see some different elements in there. it's not something that's been really well studied, and so I'm not really sure what we're gonna see. I mean, that's why, because we're getting such high resolution spectroscopy, we're hoping to be able to understand that better. I mean, Emily Levesque went on this large search for TZOs, which are red supergiants with neutron star cores.
Oh, yeah.
And was able to see some different elements, but even then, like, it was really, really faint. She needed really high resolution. And so I'm not as confident about being able to see different elements from the B star that merged. I think the rotational velocity will be more of the indicator, but hopefully we'll be able to find that out, because it's also something that hasn't really been looked at. So yeah.
Great, thank you. Well, we are now at the 30-minute mark. Let's thank Kathryn for giving this awesome talk, and I will let Sirio introduce the next speaker.
Thank you.
Also, I just mention, if you're interested to chat with Kathryn, she has lots of slots available for tomorrow. So please check out her schedule and add your name to the list.
Sounds good. So let's move on to our second speaker. We're talking about cosmology now. Just a few reminders. First, this meeting is being recorded and will be potentially posted online. If anyone has an objection, please let us know. Another thing is you can clap your hands with the tool on Zoom at the end of the talk if you like. And you can, if you want to interrupt, you can ask a question during the talk, but we prefer if you keep your questions for the end. You can either write them in the chat or just ask them with the raise hand feature on Zoom at the end. So today we have Jahmour Givans. He is a graduate student at the Ohio State University, working with Chris Irada, and he was an undergrad at Brown University before that. And he's going to talk about modeling the Lyman-alpha forest. So why don't you share your screen and go ahead.
Thank you very much, Sirio. So today I'll be talking to you all about Lyman-alpha forest perturbative modeling in particular. And at the end of the talk, I'll get into a bit how we can use this information to improve CMB constraining power from upcoming surveys. The first part of this talk is based on work I put out with Chris earlier this year. And it's important for us to break down this paper title because there was a lot going on. So over the next several slides, I will take time addressing redshift space, baryon acoustic oscillations, the streaming velocity effect, and the Lyman-alpha forest. I understand that this audience is fairly broad, so for several of you, I'm sure it'll be quite the review, but others may find it particularly informative. So please don't be shy about letting me know if I need to speed up or slow down a bit. Okay, so what is redshift space? In standard real space coordinates that we think about every day, objects are pretty much where they appear to be. So if you saw a galaxy in one position and you think it has some certain X, Y, and Z, that corresponds to the true X, Y, and Z. However, in redshift space, an object's position gets distorted along our line of sight. And this is caused by peculiar velocities of the particular object we're looking at. So again, in the case of galaxies, if the galaxy was just out there in space and not moving at all, then its Z coordinate would be the true Z position. However, because that galaxy is more likely than not moving somewhat toward or away from us, the inferred Z coordinate actually ends up changing. So this is kind of symbolized here in this bottom image, where you can see in the top row, the actual shape of the system you're looking at is perfectly circular in each case. But if you have some component of the velocity going in the vertical direction, then you see that this stretches and the circular shape stretches and becomes a bit more elliptical. And BAOs for baryon acoustic oscillations. In the primordial universe, you had this plasma of photons and baryons, and there were dark matter over densities or inhomogeneity seated throughout it. Because of this, there was this tug of war that happened between gravity, which wants to attract the fluid down into the perturbations, and fluid pressure, which wants to fight the gravitational force and push outward. And this process continued on for many years and created these standing sound waves, which we call baryon acoustic oscillations. As the universe continued to expand and cool off a bit, these waves were able to travel on the outward push about 147 co-moving megaparsecs before decoupling happens. And because of this, we have baryons that get left behind in the sort of spherical shell around these initial overdensities. And because that number of 147 megaparsecs is very tightly constrained by fundamental physics, we can use this feature as a standard ruler in cosmology. The idea is that every time we see this feature, we know it corresponds to a physical separation of 147 megaparsecs, and then we can compare that to the actual angular size we observe and get a distance estimate for the object. The Boss collaboration some years ago put out this cartoon drawing, which is basically a representation of what I just explained. Here in the middle, you have these clumps, and then there's a spherical shell around each clump. And this line here would correspond to our VAO scale, roughly. Okay, but the same physics that produced BAOs also caused other effects in the early universe. Baryons and dark matter were not moving at the same velocity at the same time, at this time in the universe's history. Instead, that velocity was actually supersonic by the time decoupling happened at redshift of about 1,000. Because it's supersonic compared to the sound speed in neutral hydrogen gas for the given temperature of the universe at that time, this speed had a more important impact on the structure formation than your standard Jeans criteria. So generally we think of mass, distance, scale, speeds, and all that being involved with when matter is able to form. But because everything was moving too fast, it was difficult for a structure to fall into the gravitational potential wells. And because this was started at the same time as general BAO physics, it's reasonable to assume, and we find in practice, that you impact the BAO scale by some amount by incorporating these streaming velocity effects. Now, I've been using galaxies as an example case, but I personally worked on the Lyman-alpha forest when it came to streaming velocity effects. So just for a brief overview, throughout the intergalactic medium, you have a bunch of neutral hydrogen gas clouds. And in the background of these clouds, you can have quasars that shine light over a wide range of wavelengths. As that light travels toward us, it can redshift down to about 1216 angstroms. And if that happens at the location of one of these neutral hydrogen clouds, you will excite the Lyman-alpha transition in neutral hydrogen. That transition sends an electron from the ground state to the first excited state. And that shows up as an absorption feature in the transmitted flux of the quasar. And because you have multiple clouds at different redshifts along your line of sight, you can have multiple different absorptions from the same, emitting quasar. And that ends up looking like this forest of absorption features that you'll see in the transmitted flux fraction. So in the cartoon image, you can see here this entire jagged region of dark black lines in between about 4,500 and 4,000 or so and angstroms, and that would correspond to what we call the Lyman-alpha forest. Okay, now why do we care about this particular probe? So it's a robust tracer structure in between redshifts about 2 and 6. We roughly think of redshift 6 as being when reionization mostly completed. And usually above redshift 2, it can be difficult to detect most types of galaxies we would care about. So the Lyman-alpha forest really covers this pretty broad range of redshifts. It also allows us to study reionization, since we mostly look at it right after the end of reionization. And subsequently, we learn about the thermal history of the intergalactic medium. As this image in the corner shows you, the Lyman-alpha forest corresponds to smaller physical scales and maybe slightly higher redshifts than most other tracers that we're looking at. And it can also be a complementary probe for data from these other probes as well. The idea is that anything we want to study in the evolution of the universe's history, We want to know basically from now, which is redshift 0, to redshifts as high as one can get to. And the Lyman-alpha force is good for helping us kind of build that bridge. Now, before understanding what I did in particular, we have to know a little bit about large-scale structure perturbation theory. This is a formalism that assumes the underlying matter field of the universe is smooth and can be described by collisionless dark matter particles. These particles follow a few different equations, in particular the Poisson equation, the continuity equation, and the Euler equations. And the idea of perturbation theory is that on large physical scales, some of these fields can be treated as perturbations onto others. For example, the density contrast, which describes the deviation of some small region of space from the mean density of the universe, is usually treated as a perturbation onto the overall cosmic density field. Similarly, if you imagine galaxies or something as being like particles, and the net motions of all the galaxies forming some type of particle velocity field, the individual peculiar velocities of one galaxy or a small subset of those galaxies are a perturbation onto that larger field. Because we can treat these as perturbations, that allows us to linearize the equations above and solve to actually determine the evolution of these fields. Now, how does perturbation theory and the Lyman-alpha force work together? So most purely perturbative models have been based on linear theory. And what I mean by a purely perturbative model is that we have some model of Lyman-alpha force that does not rely on, say, fitting functions to give you some small scale dynamics. And these linear models basically follow the representation of this top equation, where we say the flux fluctuation, which is the Lyman-alpha force equivalent of an overdensity, is equal to some unknown coefficient times the matter density field plus some different unknown coefficient times this eta field, where eta is related to the velocity divergence. So that was not quite state of the art, but it's definitely the most common thing that was used for a long time. And in my work, I introduced a complete second order model. Second order meaning that the above equation is pretty much linear, everything's just first order fields. And the second order model will take it up to quadratic orders. What made my model particularly interesting was that the arguments we used were applicable to any tracer in redshift space. So it doesn't matter if you want to look at Lyman-alpha force or galaxies, voids, or 21 centimeter emission. The fundamental ideas were applicable to all of them. And we independently derived this equation, but it resembles something else that was derived in the context of effective fields theory of large scale structure for galaxies. And if you'd like to know more about that, just ask me and I'll let you know a little bit more at the end. And there were also these streaming velocity contributions that were already known in literature. So the idea was effectively this. We use a baseline model that was taken from former literature put out some years ago to model the power spectrum, which describes the variance of the density field as a function of scale. And if you take that baseline model as is, and then you build correction pieces to it based on combinations of these bottom two equations, you can then compare the original power spectrum to this modified power spectrum. And when it comes to actually getting these unknown bias coefficients in the scale, some of the bias coefficients we were able to get from simulations that were run by Chris or other researchers. And others we had to kind of make this approximation. So we ended up using this thing called the fluctuating Gunn-Peterson approximation. That is a formula that you derive the optical depth in redshift space based on some basic assumptions about the underlying physics. And because optical depth is related to flux and the flux is related to delta F, I can combine all of this in order to calculate what I think the bias coefficients look like. And when we actually have to do a model fitting for the BAO scale itself, we do this on both that original power spectrum I told you, and then a power spectrum where you add that to the correction pieces. So we fit it in each case using chi-squared minimization. And then you want to compare the value for alpha, which sets the scale of the BAO. And you compare the value for alpha when your streaming velocity bits are present, so when BV is non-zero, and when it's not present, so when BV is 0. And the change in alpha corresponds to the shift in the BAO scale. How does that actually look? What you can see here is I plot this example case of, in red, we have the full power spectrum that I told you. Blue is just a base model where you have no streaming velocity bits. And green is the absolute value of the difference between the two. And for these scales that we're looking at the larger end of the scales, you can see blue and red are perfectly aligned. You can't distinguish these from one another at all. And it's only a little bit later on when we get to slightly smaller physical scales where blue and red begin to separate a bit. And, you know, this difference separation is much smaller than, you know, it's a couple order of magnitude smaller than the actual values of PK itself. Okay. So the results and takeaways of that paper were that the amount of BAO shifting you get strongly depends on your choice of bias parameters. And what we've done here in this table is to show mu. So that's different angles between the wave, between the line of sight and the actual value of K you're looking at, the wave vector. And 3 different columns corresponding to different choices for simulations. So in one case, we took 3 simulated values and set the other unknown bias coefficients to 0. In the second case, we just took 2 from simulations and set them all to 0. And in a third case, we took the first 2 from simulations and others came from that approximation scheme, the fluctuating Peterson approximation. And what you can tell by looking at this table of values is that this percentage shift changes very dramatically depending on which of these procedures I use and what direction I'm looking in. And why this matters is that DESI, the dark energy spectroscopic instrument, is going to be the leading probe of studying the Lyman-alpha forest in the coming years. And it's able to nail down the BAO shift, the BAO scale at a precision of 0.46%. Now, the types of changes in values you see here are all significantly less than 0.46%. But you could imagine that, you know, streaming velocities are just one source of systematic errors. If I had a handful of different systematics all contributing at about this amount, then it might be a significant source of error for DESI. And future work for this would be to go to higher orders in perturbation theory. So I told you I went up to 2nd order. Ideally, we would like to go up to 3rd order because that allows us to do much more interesting physics, somewhat analogous to QFT loop integrals, and to do a better job of determining what those unknown bias parameters are. I told you we had to use approximations and only got a couple from simulations. And right now I'm actually doing some work related to trying to understand what the other 6 or so of them are.
5 minutes.
Okay, thank you. And with these last 5 minutes, we'll briefly talk about using this in the context of CMB constraints. So one application is looking at the neutrino masses, or particularly the sum of the neutrino masses. So what happens is that in the universe, the expansion history can change as neutrinos go from being relativistic in the very early universe to non-relativistic. And any probe that is sensitive to this expansion history, such as baryon acoustic oscillations, is able to measure this effect. Another thing that happens is that the neutrino masses will suppress the late time amplitude of fluctuations on small scales relative to what you would get in the early universe. And if you compare the primary CMB, so what most people think of as a CMB, and compare it to the secondary CMB, which is basically the lensed CMB, and you look at how the power spectrum is different at small scales for each of them, you're able to determine what that neutrino mass sum really is. This is just a visual aid of what I explained. I apologize in advance that some of these colors may not be the most friendly choice for those of you who may be colorblind. So if you need me to explain it further, I will. But effectively, what you notice here is that these top straight lines are just the zero mass neutrino case. And then each line under this is increasing the total neutrino mass sum. DESI BAO information is actually able to help us break the degeneracy between the sum of neutrino masses and the overall matter density. And that BAO information comes from galaxies, quasars, and the Lyman-alpha forest. So the kind of work I did on improving Lyman-alpha forest BAO modeling should help us get better constraints on the sum of neutrino masses. And one particular forecast looks at the Simon's Observatory goal with ideal DESI BAO information and ideal Lightburg tau information to constrain the neutrino masses down to 17 millielectron volts. And if they're able to realize this best case scenario, then you could detect the neutrino mass sum in the normal hierarchy at 3.5 sigma and in the inverted hierarchy at 5.9 sigma. This is just a plot of what I explained. Depending on how optimistic your case is and your choice for uncertainty and tau, you can constrain it to either, something like 33 MeV down to like 17 MeV. And that's pretty independent of the sky fraction you look at. And the last thing I'll mention very briefly is applications to primordial non-Gaussianity. So primordial we assume in general that the universe started with Gaussian initial conditions, but there is some amount of primordial non-Gaussianity, and that's parameterized by this amplitude F and L. And that can be used to place constraints on different models of inflation. It causes galaxies to exhibit this kind of scale-dependent bias, where the linear bias coefficient scales as F and L over K squared. And the same dependence is also present in Lyman-alpha forest. And one could ask themselves whether the combination of the CMB and Lyman-alpha forest can improve primordial non-Gaussianity constraints in the same way that combining CMB with galaxy clustering data can. This is a plot looking not at Lyman-alpha forest case, but for the combination of lensing with Rubin clustering as a function of scale. And ideally, we would like to bring these curves down as low as they can get them closer to this intersection point of 1 down here. And my idea is that if we improve our Lyman-alpha forest modeling, and the clustering of it in particular, then hopefully that can help us bring down these curves and get us to uncertainties that are desirable for the next generation of cosmological surveys. And I will conclude by saying that the Lyman-alpha forest is great for studying particularly small scales at early times, but the perturbative modeling must improve to get accurate cosmology from it. We can use Lyman-alpha forest data to complement CMB measurements, including neutrino masses and primordial non-Gaussianity. And the combination of large-scale structure and CMB data will help us achieve unprecedented precision. Thank you.
Thank you for a very clear talk. And I'm sure a lot of other people like me that are not familiar with the field appreciated the introductory material. So questions, you can either ask them directly or type them in the chat if you prefer. In the meantime, I do have a very general question.
Yes.
You mentioned a couple of times how this formalism for the perturbation theory can be applied in different fields.
Yes.
And so I'm curious, because you're doing this in cosmology where, of course you have the expanding universe and all of that. How portable is all of these into or from other completely different fields, such as quantum field theory?
So the real, I guess, portability aspect is the structure of what you're doing. So we tend to, so if you do this in the context of quantum field theory, which I took some years ago, so I don't remember much of it anymore, but the types of fields and the interactions that you're being treated with have these certain properties. I forget exactly what they are, but things like locality and whatnot. As long as that's true in, say, this is also true in cosmology because gravity has, a certain range of interaction scales the same way that QED does. So as long as you are able to design your perturbative formalism in a way that captures things like locality and it's, truly perturbative, then it's extremely portable.
Thanks. That's very interesting, very fascinating. Any other question? If not, let me remind you, you can still sign up on the schedule to talk with either of our speakers. And let's thank them again for 2 really nice talks. Thanks.